Okay, so far we said that the CPU is the brain of the computer and that it simply executes instruction. No. Think. An important question arises. What instructions can the CPU actually understand? Any idea? This brings us to an important concept: instruction set architecture, or ISA. ISA, what's the meaning of the ISA, or what is instruction set architecture? It's the set of instruction that a CPU know how to execute them. Or if I want to tell it in a simpler version, ISA is the official language used to communicate with the CPU. A simple example: imagine a CPU that only understands the following instructions: addition, which can be shown as ADD; subtraction, which can be considered as SUB; loading, it means loading some amount on the variables or on the registers, stores, and jump. You cannot tell it something like calculate average, because why it cannot calculate average? Because the instruction set or the official language that this CPU understands is just addition, subtraction, loading, store, and jump. And it has no idea about what is the average that you want me to calculate. I should write a small program to calculate the average by using the instruction that this CPU understand and know about it. So the calculate average instruction is not defined in this ISA, so it cannot be implemented, or it cannot be run by this CPU. Well, an ISA is not only a list of instructions. It's important to understand ISA. I tell you at first that ISA is the set of instruction that and its names show you instruction set architecture. But it's important to know that ISA is not only a list of instruction, it also defines several important aspects of how the processor works. One of the most important part are registers. How many registers exist, and what and how they are called. For example, AX, BX, R1, R2. These are different naming of the registers. How it works with the memory, and what's its memory model. How the processor access to the RAM. Another important part are data type. What kind of data the CPU supports. For example, it's a 32-bit range integers, it's 64-bit integers, it's floating point numbers. Example, it's important so to understand some of the most well-known ISA are x86, which worked and which are mostly and vastly used by Intel and AMD processor in most personal computers. Another one is ARM or ARM, which commonly used in mobile phones and low power devices. And another one is RISC-V, which is a newer open source architecture. For example, let's me to show you a list of x86 instructions. I bring it and take it from Wikipedia, the free encyclopedia. The x86 instruction set refers to the set of instructions that x86 compatible microprocessor supports. The instructions are usually part of an executable program, often stored as a computer file and executed on the processor. The x86 instruction set has been extended several times, introducing wider registers and data types as well as new functionality. Well, it's an example which show us some instruction, its meaning, notes, and what's it, the opcode of this instruction. Well, the instruction, let's go through them one by one and explain this table in more detail to you. Instruction column. This column shows the name of the assembly instruction. ADD, its meaning is add. It means it would add to variable or something else. CMP, its meaning the comparison or compare operands which are going to compare their input. Notes. Let's see to the first row. It's written in the notes that 1 R plus equal R slash M slash IMM. Well, what is R, what is M, and what is IMM? It means if you, I'm sorry, let me to show you, can I have any access to the, no, I cannot use any laser point or another things on this screen, I'm sorry. So I was speaking about the notes section, and I want you to look at this part. The first row, the notes column. It's written that the add instruction, which means add, how it's implemented here. R means the register, M means the memory, and IMM means immediate value. It means some constant written directly in the instruction. For example, I write A plus 10. 10 is the constant value that is written directly in my instruction. Well, this means a register can be added to another register. A register can be added to a value in the memory, or a register can be added to an immediate constant. Okay, so for example, I can write add rax, 5. This means rax is equal to what's stored on rax as a register plus 5. Okay, for compare, it's similar. It's important to check that in the compare operand, this does not really store the result. It performs a subtraction only. Check it, the second row. For comparing, it just subtract register from another register, from something that comes from memory or from immediate value. Okay, and instead of saving the results or storing the result, it's update the CPU flag. There are some CPU flag, for example, 0 flag, sign flag, and other. It tried to update that flags. For example, if I wrote CMP as the compare, rax, RBX, RAX, and RBX. These are two registers. It's a subtract RAX from RBX. Okay, and the result is stored on the flag. The fourth column is opcode. And opcode is the real low-level representation. This column is one of the most interesting parts. Do you know what's the meaning of opcode? Opcode means that it's the actual code that is sent to the CPU in the form of binary. Okay, CPU does not understand the ADD. It sees the opcodes, and opcode is that binary representation. It's that low-level representation of the instruction. The actual code that is sent to the CPU is the opcode. These are some hexadecimal values that represent different version of the add instruction, because if you use the register or the memory or imitative value, each of them may have different instructions, so their opcode may be different from each one.